radicals are roots. That's what the word means. Square roots are one kind of radical. We recognize them by the funny-looking square root sign. The square root of 4, the square root of 9, the square root of 25. Fine, but what does that mean? The square root of 4 means the number which, multiplied by itself, gives 4. The square root of 4 is 2, because 2 multiplied by itself is 4. The square root of 9 is 3. The square root of 25 is 5. And right now, I want to point out something that will keep you out of big trouble, and something else that will be a big help later on. Notice first that, as we saw, 2 is the square root of 4. It is not the square of 4. That's something entirely different that goes off in the opposite direction. 4 squared, the square of 4, is 4 times 4, and that's 16. Square root of 4, 2. Square of 4, 16. Don't confuse the two of them. Just think about it for a moment. What is the square root of 4? Of 9? Of 16? Of 25? The square root of 4 is 2. The square root of 9 is 3. The square root of 16 is 4, and that of 25 is 5. Now, what about the square of each? Well, 4 times 4 is 16, so 16 is the square of 4. 9 times 9 is 81. 81 is the square of 9. 25 times 25 is 625. And 16 times 16 is whatever your calculator says it is. Clear enough? Good. Now, here's a thinking question you ought to be able to handle by now. The square root of 4 times the square root of 4 equals what? Think about it. Choose your answer, then turn on the tape again. In each case, the square root of 4 is 2. So I simplify immediately, and I have the answer. 2 times 2 is 4. So, when I multiply the square root of 4 by the square root of 4, I get 4. Because that's the definition of a square root. The square root of 4 is the number which, multiplied by itself, gives 4. So the same thing has to be true also for any other number. The square root times the same square root gives the number itself. Remember that. We're going to use it. Lots. The same thing stated as a definition. Notice that the square root is defined to be always equal to or greater than 0. It cannot be a negative number. Of course, the square roots of numbers like 4 or 9 or 16 are pretty easy to deal with. We can figure them out in our heads. But what about the ones that don't come out even, like the square root of 7? We can guess that the answer lies somewhere between 2 and 3. It has to. But there just isn't any easy way to find this irrational number yourself. So if you really need it, grab a calculator with a square root key, or find a table of square roots and look it up. Now it's time for our first discovery about square roots. And here it is. Square roots can be multiplied together or factored into their parts without changing value. How do we find that out? By doing it. Take the square root of 36, for example. We know that the answer is 6 because 6 times 6 is 36. But instead, let's factor 36 into 4 and 9. Take the square root of each of these two separately, multiply the answers, 2 and 3, together, and we get the same answer, 6. It works. If one example isn't enough to convince you, here's another one. Factor 100 into 25 and 4. Take the square root of each, multiply them together, and you get an answer of 10. And that's right. 10 is the square root of 100. Notice that this also means we can simplify algebraic expressions in the same way, by factoring. When it comes to factoring square roots, there are two right ways to do it, but only one of them works. Sound funny? Watch this. You have a number that is simply too big. You can't find it on your square root table. How can you handle it? By factoring it, breaking the big number into smaller pieces. So you factor 700 into 2 and 350. It's correct, but it doesn't work. It's useless. You now have two difficult square roots instead of one. Instead, you want to find factors which will disappear, factors which are squares themselves, numbers like 4, 16, 25, 100. Here, 100 works fine. Now we can at least simplify that part. The square root of 100 is 10. We look up the square root of 7 on a table, multiply it by 10, and we have our final answer, the square root of 700. Once again, the trick is to look for factors. But that isn't enough. Always look for factors which are squares themselves, 100 or 16 or 25, which will disappear when you replace them with their square roots. See if you can use that technique right now and come up with a simpler form of this square root. Remember, you want at least one factor which is a square. Immediately, I look for a factor of 45, which is a square. 9 is a square, and 9 goes into 45 5 times. I end up with 3 times the square root of 5, and I can use a table of square roots or a calculator to take it farther if I have to. That will give me a decimal answer, of course, but the answer is fine as it is. Now a question. Can we do the same thing with algebraic expressions? Of course we can. There's nothing to it. Every even exponent gives an easy square root because the exponent law says that you add the exponents to multiply. So, for example, the square root of x to the 6th is x to the 3rd. That last single z we have here, we have to leave alone because there's no way to take its square root at this point. Here's some more good news. We have the same sort of law for division. That makes it possible for us to take the square root of a fraction. With numbers, we do it like this. Since the square root of 4 is 2, and the square root of 9 is 3, our final answer is a simple 2/3. And once again, the same rule applies to algebraic expressions as well. Try this one by yourself. You'll need both your multiplication and division rules to help you split it into its pieces. The first thing I do is create a separate numerator and denominator without actually changing anything. Then I split the numerator and the denominator into their parts, leaving the a with its even-numbered exponent, 4, but changing the odd exponents to even, and leaving the leftover b and the leftover c on their own. Then I simplify the number part and each of the even parts, and I leave the extra b and c as is. That's my answer, because it's as far as I can go. Multiplication and division of square roots really aren't much of a problem. The rules are simple, and they work. But don't try to use the same kind of rules for addition or subtraction, or you'll be in big trouble. For example, 9 and 16 are 25, simple addition. But if we work out the square root of 25 on the right, and the square roots of 9 and 16 added together on the left, we find two different answers entirely. The whole process is wrong. So we cannot split up or combine square roots with addition or subtraction. It doesn't work. But we can for multiplication and division. We can summarize what we've seen so far into two laws for multiplication and division, and no law at all for addition and subtraction. Let's take a closer look at something we're pretty sure about, multiplication. We already know how to do problems like these. They're easy. And we know that multiplication rule works in either direction. But what if you ran into something that looked like this? If you think it looks a little bit familiar, you're right. It looks just like the distributive law for algebra. And it is. And we handle it in the same way, multiplying the parts separately and doing whatever we can to simplify at the end. Be sure to notice that the square root of 2 times the square root of 2 is 2. We saw that earlier. And 5 times 2 gives us the 10 we see in the answer. You'll also remember from other modules that we applied the distributive law to more complicated problems by using FOIL. Multiply the first, outside, inside, and last terms in that order. Let's try the same thing with square roots. Multiplying the first, outside, inside, and last terms will give us these results, all positive numbers, which we simplify wherever we can, and then write out in the usual form to give us our answer. That's as far as we can go. Here's another one of the same kind for you to work on. Use FOIL, multiply, simplify, and come back with your answer. If you have a large sheet of paper, you can write your results across the page. I list my results vertically here for convenience, but I'm very careful to keep the negative signs where I need them. And then I simplify wherever I can. And finally write it out in the ordinary way. And once again, that's as far as we can go because all of these terms are different. What if they weren't? What if some of the terms were alike? Can we gather terms by adding or subtracting the same way we do with simpler expressions like this? Yes, we can, if we're careful and if we make sure that the terms are really alike. How many occurrences are there here of the square root of 2? 3 plus 5, or 8 times the square root of 2. How many of the square root of x? 2 minus 7, or a negative 5 times the square root of x. So now you know how to add, subtract, and multiply expressions with square roots or radicals. Actually, they behave very much like the other variables we've seen. Now, see what you can do with this one. Start by checking for like terms, and then simplify it further if you can. The first thing I notice is 2 like terms I can combine into one, giving me a negative 5 times the square root of w. Then I run out of like terms, except that I see a square root of 2 hiding, you might say, as a factor of the square root of 8. And when I rewrite the square root of 8 as 2 times the square root of 2, I find one more pair of like terms and combine them for my final answer. Take it one step at a time and you'll get there, even if it is a bit tricky. Now you have your basic tool chest full of techniques for manipulating square roots. They're really quite similar to other operations you learned earlier in algebra, and they work the same way. Take a look at some more examples and see if you can get a solid grasp of all these ideas right away. And then give yourself a workout on a bunch of these problems. You'll be glad you did. We're going to see more about the division of radicals in another module, and you'll want to be ready for it. Good luck.